Nice. So we are going to start with Chapter 1, Section 1. So the battle work I have for you is what is a rational number? Okay, hopefully you remember a rational number is any number that can be written as a fraction. Okay, any number that can be written as a fraction. Okay, so we're going to be talking a lot about rational numbers later in this section. Okay, so objectives today, we're going to find the sum or product of two rational numbers and be able to explain why it's rational. We're going to look at the sum or product of rational and irrational numbers. Okay, so this is a discussion question I wanted to do with whole class because there's not really one right answer to this problem right here. Okay, you should be able to back it up whatever you think. Okay, so Cindy and Victor are playing a card game where they have to get 3 numbers of the same type in a row to win. Okay, so notice Cindy has the stuff here in red, and the Victor has the stuff here in blue. Now, you could say, okay, Cindy won because she has all rational numbers. Okay, you could say Victor won because he has all positive numbers. Okay, anything like that, you just have to be able to support your argument. Okay, so that leads us into example 1. We're going to talk about sets and subsets. So this book decides to give a problem first and notes second. Okay, so here's the problem. In the set of numbers from 1 to 10, which elements are in both the subset of even numbers and the subset of multiples of 5? So first thing I should probably say is, what is a set? A set is a collection of objects such as numbers. Okay, so a set of numbers 1 to 10, you just list the numbers 1 through 10. An element of a set is an object that is in that set. Okay, so if I'm looking at the set 1 to 10, an element would be 2. Another element could be 7, okay, something that's in there. We write a set by listing the elements enclosed in curly braces. Okay, and I typically like to name my sets because it helps keep it straight. So we name sets and subsets with capital letters. Okay, so let's start with the set of numbers from 1 to 10. I'm going to call that A. So A equals, and you just list all of the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and there's my curly braces. So then a set B is a subset of set A if each element of B is also an element of A. Okay, so a subset of A could be just the numbers 1 and 2. Okay, so it's got to be part of that set. So if we go back to the question, we want to know the subset of even numbers. Okay, so I'm going to call this B. So let's list what's in B. Okay, just the even numbers. So 2, 4, 6, 8, and 10. And then C is a subset of multiples of 5. Okay, so what are my multiples of 5 in this set? 5 and 10. Okay, so now that I've got all the sets and subsets listed out, the question asks which numbers are in both of my subsets. Okay, so what's both in B and C? Okay, you should say one number, 10. So the answer to this problem would be 10. Okay, and you list it in curly braces because it's still talking about a subset here. Okay, so that's the kind of work I would expect for a problem like this. Hey, you try. Please take a minute, pause the video, and try this problem. Okay, in the given set of numbers, which elements are both in the subset of numbers divisible by 2 and the numbers divisible by 3? So numbers divisible by 2, let's call that B. Okay, so 6 is 5, no, 6 is. Okay, so divisible by 2 is basically saying the even numbers. Okay, and let's call the numbers divisible by 3, let's call that C. Okay, so multiples of 3 would be 6, 9, and 12. What problem asks, though, which ones are in both? So I've got 6, and I've got 12 in both. So my answer, that's a really bad curly subset, curly brace, is just 6 and 12. Okay, hopefully you did well in that problem. Okay, example 2. We are playing a math game where I need to put a set of 3 cards in numerical order. My cards show 40 over 11, the square root of 324 over 36, and the square root of 10. We need to order the cards from least to greatest. Now, looking at these numbers, do you have any idea? Say, I personally don't. Okay, so when we have a problem like this, the best thing to do is to find the decimal equivalent for each number. Okay, so I'm going to go ahead and pull up my calculator here. I should have gotten it out before I started. Okay, calculator right here. There we go. It's coming slowly. Okay, so let me just clear everything I have here. Okay, I'm looking at 40 over 11. So I'm just going to type 40 divided by 11. I get 3.636 repeating. Okay, so I'm going to round it to 3.64. Okay, so 3.64. Next thing we do is the square root of 324 over 36. Okay, now this calculator, to get square root, second x squared. Okay, it's the square root of 324 divided by 36. Okay, and make sure you keep that divided by 36 completely under the square root. Okay, there is a difference there, so be careful. Oh, that just gives me 3. And lastly, we want to know about the square root of 10. Okay, so second x squared again, because notice the square root in blue above it. Square root of 10. 3.16. Okay, so it should be pretty easy now to see which one's the smallest and which one's the greatest. Okay, so I'm just going to write them in order, least to greatest. So my smallest was this one. Okay, and that was equal to 3. However, I don't want to put 3. I want to put the end number they gave us. Okay, so the smallest number we have is the square root of 324 over 36. Okay, the next smallest, square root of 10. And finally, 40 over 11. Also, with these problems, you should be able to plot these numbers on a number line. Okay, so with this, you want to make sure you put a scale. Okay, so I'm going to go with 2.9. I'm going to go by 1.1. Okay, so 3.1, 3.2, 3.3, 3.4, 3.5. And then I'm just going to plot them. Okay, so 3.64 was 40.11. I got to extend my line a little bit here. So 3.5, sorry, I wanted that being blue, 3.6, 3.7. Okay, and I should be good now. Okay, so we know that was 3.64, so that's somewhere about right here. And that was 40 over 11. Next one I had was a square root of 324 over 36. That was just equal to 3. So square root of 324 over 36. Then finally, I had the square root of 10 at 3.16. So that's about right here. So if I ever ask you to put them on a number line, come up with a scale and keep it even, and then put the numbers where they belong. Okay? You try. Please turn these to decimals and list them in order from least to greatest and put them on a number line for me. Okay, pause the video and try that. Okay, so 60 over 6, square root of that. Again, notice I have the over 6 in the side of the square root. Oh, that's just a square root of 10, 3.16. Okay, let's look at the square root of 82. Ooh, 9.055, so 9.06. Hopefully you don't need a calculator for pi, it's just 3.14. Okay, so if I put them in order from least to greatest, I have pi, square root of 60 over 6, and square root of 82. I put these on a number line. Okay, my scale is going to be quite large because I start at 3.14 and I go all the way up to 6. 3, or all the way up to 9, sorry. 4, 5, 6, 7, 8, 9. So if I plot these, smallest is pi, so 3.14. I'm doing different colors because these are so close. So square root of 60 over 6. And then finally, square root of 82 is 9.06. And that's how you do that one. Okay, one more problem. Please try these. So square root of 9 over 7. 1.13. 8 over 3. 2.67. And 54 over 7. 7.71. Okay, so these are in order already. Okay, so that is my order. So let's go ahead and do our number line. Okay, I'm going to go by ones again, probably because those are awful close together. 1, 2, 3, 5, 6, 7. Okay, 1.13 would be about right here. So square root of 9 over 7. 2.67. So that's 8/3. And 7.71 would be 54/7. And that's how you do those. Okay, next problem, talking about rational numbers. So is the sum of two rational numbers always a rational number? Well, let's talk about what is a rational number. Okay, so remember, a rational number is any number that can be written as a fraction. Okay, a more formal definition is any number that can be written as the quotient of two integers. Okay, so integers are positive and negative whole numbers. Okay, so notice I have dot, 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 and then -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Those dot, dot, dots means they go on and on forever. Okay, so those are the integers. Whole numbers, 0, and the counting numbers. Okay, so counting numbers, think about it when you teach a little kid how to count. You start at 1, go to 2, 3, 4, and so on. Okay, so our whole numbers are 0 and the counting numbers. And finally, we have the natural numbers. There are counting numbers, 1, 2, 3, and so on and so forth. And those all kind of go together. The other type of number we're going to talk about in this class are irrational numbers. Irrational numbers are numbers that cannot be written as fractions. Okay? So an example here would be like pi, square root of 10. Okay, something that goes as a decimal on and on forever. Okay, you cannot write it as a fraction. So with these, I often will do some shorthand sometimes. Okay, so mathematicians use a lot of shorthand when they're taking notes. So the rational numbers often are denoted by R with 2 lines. Okay, the integers are often denoted as Z. Whole numbers are W with an extra line, and the natural numbers are N. Okay, we really don't say anything about the irrational numbers. The thing I want to draw your attention to now is this Venn diagram here. Okay, these are all real numbers. Oh, I'm sorry, rational numbers. This is real numbers. Okay, rational numbers, we use Q. Okay, this is real numbers. Okay, which in this class, all we look at is real numbers. There's actually something called imaginary numbers, but you'll talk about that in Algebra 2. Okay, so everything we work with is real numbers. Okay, so notice the Venn diagram includes all of this. Okay, the irrational numbers and the rational numbers are all grouped in. Okay, those two don't overlap at all. You're either rational or you're irrational. So the rational numbers are where we get interesting. Okay, notice in this rational numbers, we have 3 more circles. Okay, the biggest subset of rational numbers is called the integers. Okay, notice whole numbers are a circle inside of the integers. Okay, so if I'm a whole number, I'm also an integer. Okay, natural numbers are the most specific you can go. So if you're a natural number, you also are a whole number and an integer and a rational number. Okay, so when we talk about sets of numbers, they can belong to more than one subset. Okay? So, going back to that question, is the sum of two rational numbers always a rational number? Well, let's think about it. We can try several different cases. Okay, if I add a fraction, am I going to get another fraction? Absolutely. 1/2 plus a third is 5/6. 7/8 plus 3/4 gives me 13/8. 11/5 plus 1/6 gives me 71/30. Okay, you should be comfortable with adding fractions. Remember, you got to get that common denominator. And then it's pretty easy to see that you still get a fraction. Okay, so in this case, the sum is also rational. But you cannot try every pair of rational numbers since there are infinitely many of them. How can you know whether it is true for all rational numbers? So what the book wants you to do is to use variables to represent any rational number. And they actually go through something that is a proof. I personally think this proof is a little too much for algebra. So I'm going to skip the proof, but you should know that a rational plus a rational always equals a rational number. Okay, that's the big thing I want you to know. Rational plus rational always equals rational. Okay, so then they want to talk about rational plus an irrational. So this would be something like 2 plus the square root of 10. Is that going to be rational or irrational? Well, if I throw it in my calculator, 2 plus the square root of 10, I get a decimal, and that goes on and on forever. Okay? So to me, that looks like it's going to be irrational. Okay? Big thing to take away here, rational plus irrational will always equal irrational. Okay, rational plus irrational equals irrational. Okay, they also want you to think about products. Okay, so products work just like the sums do. Okay, so product means multiply. So if I do rational times rational, I get rational. Same thing with rational times irrational, I always get irrational. Okay, so just some things to think about. Here's your homework for tonight. We're going to be on page 9. I'd like to do problem 16 through 33. If you have any questions, make sure you're prepared to ask in class. Hope you guys have a good day.